All right, so now let's do a bunch of computer exercises, kind of, get our brain juices flowing on how to make sure that we can do efficient computation with these discrete dynamical systems. So what we're going to do in order to define something that solves a discrete dynamical system is we'll define a higher order function. So a higher order function is just a function that takes in a function, right? So what is something that solves a dynamical system? Well, a function that solves a dynamical system is a function which takes in f, an initial condition, and how many steps to do, and it steps that dynamical system n times, right? So here what we're also going to do is we're also going to have a parameter p, so that way we can kind of put these parameters into the dynamical system. The reason why we're doing this is because we're going to start playing around with this parameter and see how the behavior changes. So here I'm going to evaluate it. So in Atom, you can, if you highlight what you want to evaluate and then you do Control Enter, it'll evaluate that whole thing. Here I put a doc string above, so this is just I'm forgetting the name right now. This is why it's really good to have a live lecture. Someone just mentioned apostrophe, yes. So you 3 apostrophes, and then you write down the system. A single backtick here means that it's code. 2 backticks means that it's a LaTeX. And this will actually render, for example, inside of documentation as LaTeX if it's in between 2 backticks. You can also make sure that you use 3 backticks math in order to write longer form LaTeX if you want. And so here I describe what the function does, and if you type in solve system into the help, it will demonstrate. It will show the help. Right, so this is what I'm using to be able to solve the dynamical system. It's a higher order function because one of the input variables is the function f itself. And now, is this going to be fast? Well, type stability, auto specialization. This is everything that we discussed in one of those last lectures. Now, why would this be something that should be fast? Well, because if you auto specialize, then as long as you can know what this function is, then you can inline this function and make sure that it's as fast as if you were to written this code directly. And why would it know how to inline this function? Well, it's because the type of every function is unique, right? Because the type of every function is unique, this means that solve system will generate new code for every single new dynamical system that we put in. So that's a nice way to that's a quick demonstration that this code right here should already be pretty optimal, at least on scalars, right? We're going to have to do a lot more to do caching and everything on a larger dynamical system. So let's look at this scalar dynamical system, right? So a quick check. Let me kind of delete my answers here really quickly before anyone notices. So if you start with the value 1 and you have a parameter p equals 0.25, can you guess without solving the system what will happen after 1,000 steps? So let's do the math out, right? So we have f of u equals u squared minus p times u, where u equals 0.25, right? In order, what we know from our previous lecture, or from the previous part of this lecture, is that in order to understand how the system will work after many steps, we look at the asymptotic behavior. This asymptotic behavior is given by the linearization, so we need to find the fixed points and we need to find the derivatives at the fixed points. So what are the fixed points, right? We want to solve, that means that we want to solve 0 equals u squared minus pu, which has 2 solutions, right? Because this is going to be pu equals u squared. And so this is going to have the solution that is, so we have the solution which is u equals 0, and we have the solution u equals p, right? Yeah. So those are our 2 solutions, right? Because when you plug in u equals 0, then you get 0 back out. And then when you plug in p, then you get p squared minus p times p equals sorry, did my analysis wrong? No, for a discrete dynamical system, I was thinking continuous. For a discrete dynamical system, what we want for a steady state, right? un plus 1 equals f of u sub n, what we want for a steady state, u star should be u star equals f of u star, right? So let's plug in, so what we want here is we want the output of when we apply f to u, we should get u back out. This is what we want to solve for, right? And now what we do is we move this to the other side, so we have p plus 1 times u. And so a lot of the analysis is the same, except so now we have that u equals 0 and u equals p plus 1. Oh wait, let's see. Yeah, so either 0 works or we divide by u, and when we divide by u, then we have this, right? So either u equals 0 or u equals p plus 1 are the two solutions to this system, right? And those are the two, those are our two steady states, right? Now let's look at our derivatives at the steady states, right? Because the derivative being less than 1 is going to be our indicator for whether or the derivative in norm being less than 1 is the indicator that it's stable, right? Whether values go towards it because it's a contraction mapping nearby, and therefore by Bonhoeffer's fixed point theorem, right, you'll be moving towards that fixed point. So let's look at, f prime of 0, which is going to be, well, let's first actually write out what f prime of u is. This is going to be 2u minus p, right? And so then f prime of 0 is going to be equal to minus p, and f prime of p plus 1 is going to be equal to 2p plus 1 minus p. And so this is going to be equal to plus 2. It's going to be p plus 2 if I'm doing all my arithmetic right. Yep. So okay, so let's so if we have p equals to 0.25, then f prime of 0 in norm, right? Remember, it's the norm that matters, because we're always looking at whether it's contracting, right? So we're always looking at distance functions. The norm of f prime is less than, well, that is going to be equal to 0.25, which is less than 1, right? While vert f prime of p plus 1, vert is going to be equal to 0.25 plus 2, which is equal to 2.25, which is greater than 1, right? So what this means is that at the point 0, you have a stable fixed point, and so points will go towards this one, and at this steady state, you have an unstable fixed point, and points will go away from it, right? So let's look at this computationally. So let's say you start at 1, and we have this parameter. What happens? Well, so if you start at 1, then you're at 1, you take one step, you're at 2, oh, so yeah, I started this. So 1 here is actually doing 0 steps. So with 0 steps, you're at 1, 2, now you go to 7.75, 3, 4, you can take this all the way down, and you get to 0, right? So this is essentially what we showed right here. You're going to be attracted to the point 0 because its derivative is less than 1. So that's a contraction, right? And we can show this analytically, and we can see that, when you're any of these values kind of nearby, you're also going to be going to the 0. Now, if you're at the point 1.25, which is p plus 1, right, this is our other fixed point. And so no matter how many steps you take, you're always going to be at that point. And what happens if you're a bit higher than 0.25? Well, it turns out that, now you're going to be in a region where, your derivative has now gone above 1, and so doing one step is going to grow the point a little bit, right? And then a second step is going to grow it some more, third step is going to grow it some more. If you keep on pushing this out, then you're going to be going higher and higher until you go to infinity, right? And actually we'll approach infinity quite fast, because how fast is it moving? Remember that when we did these derivations, in a linearized sense, it's moving to infinity. Like, un plus 1 is like alpha to the n u sub 0, so it's moving exponentially fast to infinity. So let's double check. So this is what I just did out by hand. As you do more and more steps, you quickly go off to infinity. So now let's start to look at these multi-dimensional dynamical systems, right? So here, for example, is the Lorentz equation, where what we have is we have a system of 3 variables and 3 parameters, where n plus 1 equals u equals the first term plus you can read this off, right? So this is a 3-dimensional dynamical system with 4 different parameters, and when you solve this system for 100 steps, you get something that is just it's almost random. We can see what it does by saving a bunch of points, right? So instead of using solve system, which only gives us the last point, let's define a new thing called solve system save, which is going to create a whole vector of output points. And then we can get 1,000 different output points. And then we can ask for example, what is the first value over time? So then we can go through that vector of vectors, grab the first value each time, go through the vector vectors, go through the vector vectors, and plot x versus y versus z, and this is what you get out. So this is actually the famous butterfly attractor problem. So this is actually one of these examples of a chaotic attractor. All right, now let's look at a few closer details at the implementation. Right, so when we do, here we had this solve system save, which we used to be able to generate the plot, right? So what it does is it creates an output vector u, where it then stores all of the time points in, and it outputs this for us, right? Now let's do one that is push, right? So what we do with the push version is we only create space for one thing. We put the initial condition in there, and each time we push to increase the size of this vector, right? So solve system save solves in that amount of time. Let me actually change this to benchmark tools to be able to get something that's a bit more precise. B time here. Now remember that if you're not using benchmark tools, the first time you call a function, you're going to be compiling the function, and so let's actually see that out. So this was let's keep this in the REPL. So here the first time you call the function, you have a larger time, because remember that Julia will JIT compile the function on the first call, and then on the second call, this is the JIT compiled version, which is much faster, right? So here when we beat time, before we had 24 microseconds. Now let's see what happens with the solve system push. Doing the same computation. It's 29 microseconds, right? So we, by pre-allocating the rest of this array, for 1,000 items, we went from 24 microseconds to 29 microseconds. And if you're familiar with something like MATLAB, where it allows you to index on the end and continually add one to the length of your vector, this sounds weird, right? Because if you do this in MATLAB, it's like 100 times slower or something, right? So why is this so good, right? That's a question you should be asking. Like, it's not perfect, right? So we created a vector of 1, we pushed, we made a vector size 2, vector size 3, vector size 4, and then went to vector size 1,000, and then outputted that. That wasn't able to get perfectly the same cost as if we started it as a vector size 1,000 and then we just added pieces to it, right? But it got very close. Got surprisingly close. Why did it get surprisingly close? And the reason for this is that it actually amortizes its cost, right? So when you first ask it to push, from 1 to 2, it will create a vector size 2, and then it will do that, right? And then what it will do is that if you try to ask it to push again, it will create a larger vector. It will go to like 4, right? And it'll let you push 2 times until it finally goes, okay, well, if you're going to push some more, I'm going to go all the way to 8. So that what I'm describing is the doubling version of this, right? Where, if you're at 16 and you ask to push once, then you will internally allocate a vector of size 32. You tell the user what you gave them back was an array of size 17, but when they push again, you don't actually create any more memory. You already have pre-allocated this, size 32 vector. Keep on changing your type information so that way it looks like it's growing until you get to 32, and then you actually have to grow it again. And the reason for doing this is because you can actually prove that you only have an O of 1 cost on average for pushing if you do some kind of growing mechanism that is called amortized like this, right? So instead of doing the growing every single time, you do bigger growths every once in a while, and that will kind of keep some of the computation from happening. There is some very long theory about what is the growth rate that you should choose. And actually, you can prove that some optimal growth rate is the golden ratio. Big surprise, like that number shows up a lot of places. And I'll put a link into the course website if you want to read the whole discussion about how do you end up with the golden ratio here. But in general, if you want just a quick and dirty version, the doubling one works fairly well. So you don't need to worry too much about using push, right? It's not 100% optimal, but because of amortization that's going on behind the scenes, it is not too bad of a solution. So let's look at what happens. So this is all with vectors of vectors, right? And vectors of vectors are a little bit odd to deal with sometimes. So for example, let's let A be a vector of vectors. So A of 1 is a vector, A of 2 is a vector. If you wanted to get the time series of the first output, though, right, you had to do something a little weird. So sometimes it could be easier to work with matrices. One way to be able to get a matrix out of a vector of vectors, this is kind of like a nice trick to remember, is you can do, for example, reduce by hcat A, and then this will build, so this will do horizontal concatenation, and it reduces it along each of these different vectors, and so this will horizontally concatenate all the different vectors. Right, so you can turn these into a matrix at any point, but let's say, if you want to give the user a matrix, why not just be filling a matrix with one of these algorithms? Right, so let's actually look at the cost difference here. So let's evaluate this whole function, and let's at p time this solve system matrix, right? So we went from 24 microseconds to 29 microseconds. Let's see how the matrix performs. And the matrix doesn't perform well, but we went up to 2001 allocations, right? How many allocations should we have if we're solving a dynamical system and we're outputting 1,000 points? Well, since every single point is a vector, right, we need to save a vector for every single point that we're outputting to the user, and so therefore we should have 1,000 allocations, right? And so here in this one we have 1,010 allocations. Those extra 10 come from the growing of the vector, the amortization that's going on in the background. The other form only has 1,001, where the 1 is due to this out, so we have 1,000 arrays that are put into this array of arrays. That array of arrays itself is the one, that last allocation. So here, when we directly compute a matrix, right? So here, what I'm doing is I say U is a matrix where every single column is going to be of length U0 because every single column is going to be my dynamical system. And so I say, the first column is my initial condition. Now compute on the first column, or compute the second column, compute the third column. And this has 2001 allocations, right? It has double. Why does it have double the allocations? And why is it twice as slow? Well, the reason is because this right here, remember, is a slice. And so because this is a slice, remember that will create a new vector for the ith column of U, right? Which is not what we want. If we're doing a computation on a dynamical system and the contract that we have with the user is that they won't modify you, then it's perfectly safe to give them just a pointer to the existing value of that existing row of our output matrix, right? So let's not create a new array. Let's actually point to that same array of the output matrix, and that's done by using a view. Remember from that first class. So here what we do is we now define and time this view. And will it be faster or will it be slower than using a vector of vectors? And we see that we're at 31 microseconds. So it's actually slower than using a vector vectors. And the reason is actually kind of very subtle, right? Because remember back to that first lecture that when you represent a matrix in terms of a just real memory on the computer, it really just is each column going down as one linear vector, right? And so if the computer is trying to optimize this for you in the background, what it's assuming is that after you want the first column, you're going to want the next column, the next column, the next column. But in reality, in the way that we've written this algorithm, the columns in the future are junk until we fill them, which we'll be filling them in here. So it's going to be pre-caching a lot of the values in the future of that array, right, for the next columns. But we don't ever actually want to use those values because the way that we're creating this matrix, they're undef values, right? They're undefined values. They're not values that make sense until we actually fill it in. And so because of this matrix structure that we've chosen, the computer will be pre-caching values that we don't use and actually causes more memory pressure, actually slows down our computation. Which I guess, it might be a little bit unintuitive. So this is actually a case where creating a bunch of smaller vectors for the computation is actually faster than creating and directly using the matrix that you might want to use for the analysis. It's just like it's a kind of thing to keep in mind, right? Now, let's actually start to look at other cases here, right? If we don't want to have a future inside of this matrix, right, because we don't want to have our cache lines, well, let's say we're going to keep on growing a matrix, right? So here, what we're going to do is we're going to define a matrix, right? So here, what I'm going to do is I'm going to define that doesn't look right. How did I find U0? Oh, so yeah, it's because I defined U0 in a different way here. So U0 equals this. So here I want to define a matrix where I start with only one column, and then I hcat, so I horizontally concatenate the next array, the next array, the next array. Kind of like what I did when I did reduce by hcat a, right? So in this algorithm, what I'm going to do is I'm going to start with a matrix of one column. I fill that one column with U0, and now what I do is I calculate the next column, and then I horizontally concatenate that onto my previous matrix, and I use that to keep on growing my matrix. In this case, I will never have a cache line going forwards. No unused values. My computer should be happy, right? And by given the amount of time that it's taking here, you should probably start to guess that, yeah, this is by far the slowest approach. It's 1.2 milliseconds, right? Everything else we're measuring in microseconds. And so why is this so slow? Well, it's because remember that a matrix itself is one amount of memory. And every single time that we create a new matrix, we're going to have to allocate an entire new vector of the full size. So the first time we allocate a vector of size 3, next we allocate a vector of size 6, we move over the first 3 values, and then we move over the new 3 values, right? Then we allocate a vector of size 9, and then we move over the first 6 values, and we put in 3 new values, right? We keep on doing this repeatedly. This is going to be by far the slowest operation because we really want to have one object that we keep on changing. So why did the vectors of vectors work so well, right? Because it's allocating a lot of small vectors. Why would it do better than this thing of growing matrices? So the reason is because remember that a vector of vectors, right? The type that you're actually putting into this vector of vectors, you're not actually putting the memory into it because the memory is on a vector. the vector of vectors itself is a vector of pointers. And so increasing its size and everything like that is very cheap, because a pointer is just a 64-bit object, right? So you're not really doing many operations to change the size of this vector of vectors. You just are finding, what you're doing in the background is you're finding a bunch of very small, length 3 vectors all over your computer, and then you're just saying, yeah, point to this one, point to this one, point to this one, and you're dumping off a bunch of memory on every single spot you can find with pointers to those little pieces. And so vectors of vectors are actually a fairly efficient way to generate outputs for a dynamical system, though because you have pointer indirection, right? To look at the first output, you don't actually go directly to the value, you go to the value to a pointer to the value, right? In this case, the analysis will be slower, but the saving from the dynamical system will be faster. So there are these fine details that you should really think about when you're thinking about how to build a program that is going to be optimizing for different conditions, right? The vector will be faster in some respects, but in other respects, it'll actually be slower. And so you might actually want to do this, this computation where you change it to a matrix before you do a real analysis. How much does that cost? The cost of actually generating this matrix in one go is 10 microseconds. So it is if what you want in the end is to get the full matrix, right? We could do that directly in 31 microseconds, or we could build the vector of vectors in 23 microseconds or 24 microseconds and turn it back into a matrix in 34 microseconds, right? So if you want the matrix, it's slightly quicker to directly make it. But if you can use the vector of vectors, it's quicker to use the vector of vectors, and it's almost the same to then generate the matrix from that vector of vectors. So I think that the most important thing is to start understanding the relationship between these mental models of hardware and start being able to predict which of these different configurations will be faster or slower in all the different conditions. Because when you start putting all these together and just mentally choosing the fastest every time, that's how you get a very fast high performance computation, right? The way that I've heard this described before is that performance is really death by 1,000 cuts, right? That a fast computation isn't done by a computation doing something really smart. It's by not doing a bunch of dumb things. All right, like the way that you have something perform fast is it doesn't perform slow. There are 1,000 things that you can do to slow down your program. Is really avoiding the slow things that really gets you most of your performance. There are some very in-depth things you can do, for example, with SIMD and GPU computing kernels. But in general, for most computations you do, it's really just avoiding things that make your program slower. So now, how could you try to make this faster? Well, let's actually do an in-place approach. Like let's do an in-place non-allocating function. So here we have the same equation as before, but instead of making this function, right, so instead of writing this function in such a way that it outputs a new vector, I could have it mutate a vector, right? Because that will decrease the number of allocations and I can make things go super zoom, right? So let's have this allocating version where what I do is I create this cache array, right? And I stick the initial condition into my output array to start. And what I do is I modify the cache array and I add this cache array to the output. And I just keep on doing that looping over. So if I'm to time this thing should be super baller, right? It should be really fast. Right, it has 3 allocations. Where did these allocations come from? We have 1 allocation for the vector of vectors, 1 allocation for the cache, and I think this last allocation is probably just the output. Right, so it's 3 allocations. This thing is twice as fast as what we had before, and the output is completely junk. Right, why is the output junk? Is there a way to be able to keep the speed and fix the output here? No, it's just not possible. Why is that the case? Well, because we actually want to give the user, right? We want to give the user 3,000 points, right? we want to give the user, 0.1, 0.2, 0.3. We want to give them 1,000 time steps and the points at all those time steps. In order to give the user that many time steps, you have to allocate at least 3,000 points worth of memory somewhere, right? This is trying to cheat. This allocates a pointer to a bunch of pointers, and then it allocates a cache vector, and it tries to continually reuse that cache vector, and it changes the pointer of the ith object to that cache vector. But as I've now just described it, right, these are all pointing to the same cache vector, and so if you update the cache vector here, you've actually updated all of your previous pointed pieces of memory to it because it's all the same vector. So you can't cheat, right? You can't make it allocate less than what you actually need. This actually has a bug in here because all of these vectors are not only the same values, they're actually all pointing to the same vector itself. Let me actually kind of demonstrate this a bit more. So let's say b equals the output here, and let's do b of 2 equals 0.2. B of 2 of 1 equals 0.2. And if I look at b again, you see that I've updated all of the arrays at once, right? These are all pointing to the same memory, and so it's actually cheating, right? It's cheating and it's getting the wrong answer. So in order to actually use the mutating form here, what you're going to have to do is you're going to have to create a new array. So you could use the mutating form, but if you use the mutating form, then you're going to have to copy before you put that pointer in, right? So you're going to have to create a new array with a new pointer, and then you say make this point to this new array. And of course, if you're to time this, you will have nullified your advantages from the mutation, because now you're still going to have to allocate that new copy. So, and what it really means is that if you actually need to output all points, the best thing that you can do is to be allocating. Really, where you can start to save is that if you know that you don't need all these intermediate points, then this kind of mutating form, where you're only then doing the copying at the output points, is what's going to be the fastest form, right? So you want to do a mixture of copying and creating arrays to be able to create saved outputs, and we want to mix that with something that has a cache on the inside. So let's see. So yeah, so if you only want the endpoint, right? If you only want what is the value of the system 1,000 steps in, then you can use all these caching ideas, right? So here I can say, well, I have this cache du, and I have my current value u. What I'm going to do is I'm going to take un, I'm going to use that to calculate un plus 1, and then what I'm going to do is I'm going to make un, I'm going to make my current value be equal to my future value. I'm going to repeat. Now I'm going to update what my future value is. I'm going to make my current value equal to the future value, and then I repeat, right? This is something that will only allocate 2 vectors for this entire computation. And so it's only able to spit out what the last point is because it doesn't create enough vectors to actually hold all the save points in the middle, but this will be much faster than if you're to solve the system in another way. So let's actually time this out. So if you were to solve the system and do all this extra saving, right, you have a bunch of allocations. And so even though solve system is this version that didn't have the cache in there, even though it was only outputting the final time point, because it was creating new vectors at every single step, in a way that is conducive and most efficient if you actually wanted to save the vectors. If you actually only wanted the last output, then it is almost twice as slow as what it needs to be, right? So what this really means is that you really should be getting used to writing this caching style. And then when you are thinking about how to write your programs, especially with large parallel programs, you should only save exactly the outputs that you need. And with a nice caching style, that will be by far the most efficient approach to the computation, right? So even as simple as just writing a loop is now 2 times faster by having a cache and in-place modification. You can actually make this a little bit better as well. So here I'm actually writing that, I'm making du be the future value, and I'm making a u be the previous value, right? And then what I'm doing here is I'm saying that u should get the values of the previous one, and then we keep on going, right? Now, why should we be updating the values of u when we have an array that already exists that is the future values, right? So we don't actually need to loop through and make the values of u be equal to du. We just need to change their pointers, right? We need to make u point to the memory that is your future values, and we need your future values to point to a cache that already exists, which is your previous u. Right, so the way to be able to write this is you actually can say u du equals, remember the value of an array is its reference itself, and so this is something that will flip the pointers. Right, so let's actually see this in action. So we could say a equals 2.0, b equals 3.0. Right, if we say ba equals ab, what this will do is this will now flip the pointers, so that way there is no actions on the values happening. Now b points to what a used to point to, and a points to what b used to point to. And this should actually be much more efficient, right? Because it gets rid of an O of 3 operation that's happening every single step. So let's actually time out what this is like. And this gives us the same values that we had before, right? But the efficiency should be quite a bit more. Actually, in this case, it is not as good. Oh, never mind. I was timing the wrong system. So it was solve system mutate. So this is now the mutating version where we've gotten rid of a lot of the computation by using a pointer swap. And here we've gotten it down to 5 microseconds, which is even twice as fast as the version that had the broadcast in there, right? So there's all these different tricks that you could do. This is probably the most efficient form for doing this, where what I'm doing in the background is I'm just always changing pointers, so that way the array that has the most up-to-date value, I'm now pointing that to be the one that I use inside of my function, and the array where I no longer need the values that are inside of it, I turn that in my cache vector, and I keep on doing my computation. This is 4 times as fast as the naive approach of doing it. So that these are the kinds of things you should be thinking about before you even start to do, optimization of the parallelism itself, right? Because these things will, a parallel code will speed up your code quite a bit. But if you do 4 times as fast as your most efficient parallel code, then it is still a much faster code, right? We can still even do much better, right? So we can use the static arrays. So remember from that previous lecture that a static array is an array which is of fixed size and is stack allocated because the function is actually compiled to specialize on the size of the array that's in here. And so it's actually more like a tuple than it is like an array, right? It's something that lives on the stack. There's no pointers to it, and it acts as though it's just an inline set of 3 numbers, which are, float 64, float 64, float 64. It acts like it's actually just one bigger number with some semantics on top of it. So here I'm going to use static arrays, and here's the static arrays version of that same function, right? And remember that when you use static arrays, you have to use them in a way that is non-mutating because they're an immutable object. But that doesn't matter because they're stack allocated, so you can create bunches of them without ever creating pointers to different spots in memory. So if we look at what happens with our with the version that is saving a bunch of static vectors, right? So remember that we want to save the system at a whole bunch of different points. It took us 22 microseconds with vectors of vectors, but now we actually have a vector of static vectors where we're just filling all these new static vectors in, and this is about 3 times as fast as the vector of vectors approach. Why is it doing this? Well, because this doesn't have the issue of the matrix, so there's no cache line in the future, but also this actually is an object that's similar to a matrix, right? Because, a vector of static vectors, like, if A, B, C, D are all static vectors, then this thing acts like it is a vector where I have this is a longer number of three numbers, then the next thing next to it is a longer number of three numbers. And so this actually acts like it's actually one vector of 3 times 12 numbers. And so it is essentially the same thing as a matrix. In fact, you can, in Julia here, I'm going to forget the syntax, but if you have a vector of static arrays like this, you can use the reinterpret function, right? Where reinterpret changes the type information so that way this vector of static vectors is actually a matrix, right? In memory, they're exactly equivalent, and so you can actually do the transformation between a vector of static vectors back and forth to a matrix without actually having to create any new arrays, right? It's just purely type information and interpretation of a set of 16 numbers that will change it from 4 by 4 to a matrix. So that's one thing to keep in mind, right? You can use static vectors to be able to make these computations that are out of place or non-mutating. You can make them fast if they're small enough. But you can also always go back and forth between matrices and static arrays to be able to get specialization on the small size, but then note that a vector of static arrays is actually equivalent to its underlying matrix in the bit form, and so you can always reinterpret the information without doing any actual operations. In LLVM, this reinterpret operation actually becomes nothing, right? Because literally it's just the same pointer doing nothing. It just changes how Julia is interpreting your code and what kind of code it's generating. So this is actually useful for a lot of getting you a lot of optimizations like SIMD and such. But remember that when we're doing a bunch of indexing operations, in order to get more optimizations, we usually want to turn off bounds checking. Right? We want to tell it that we know that our array is size 3. We're only going to be using the memory that's given to you. So please don't check for an error, because remember, an error has to check a conditional, and conditionals are like 10 times the cost of pluses and multiplies. So just the fact that we're doing, just doing one check of the conditional here is actually more expensive than a lot of the arithmetic. So let's see what happens when we change to solve system save with the version that is doing at inbounds here. So here, we are creating we're solving this whole system. We're only allocating 2 things. Well, the one thing that what we're allocating is, we're allocating the output itself, but and its output is this vector of type of U0, which is static vectors. So it's a vector of static vectors where we keep on filling in the static vectors, right? So we've pre-allocated up to n. We're going through the loop. We're adding static vectors to here. And each time that we call f, we're now turned off bounds checking. And by turning off bounds checking, we get a bit more performance, right? We're about 50% faster than from where we were. And now let's say we only needed the final point, right? If we only needed the final point, then what we can do is we could just loop through and keep on creating new static vectors, right? And in memory, this is actually just putting values on the stack and then reusing them. So there's actually 0 memory that's going to be used here until the very end to allocate the output static vector. And so we should actually see 1 allocation for that output, which is exactly what we see. And it's a little bit funny that actually this ends up being a little bit slower. I mean, that might just be because we're kind of butting up against the, how fast the computation actually is. This one might have been a bit faster. I wonder if my video equipment and stuff are kind of getting in the way here. That's a bit curious. So yeah, let me, homework. Just go figure out why this one is actually slightly a bit slower. That's a fun little detail. Yeah, it would take me a little bit of time to figure out what it is. So if you want to go check it out, that'd be a very nice thing to dig into. But the theory says that they should actually be about similar, right? This vector static vectors is the only thing that you're really adding to the computation when you're saving all the outputs, and that allocation itself is a bit costly, but it shouldn't be overly costly. but it shouldn't be negative, right? So there is something to figure out why this computation is faster, and why. Oh, did I actually mix up why this computation is faster and why it's taking more memory is a very good question that I won't debug right while I'm live because live debugging sounds scary. So lastly, we can make a saving version that is completely non-allocating, right? So how can we do that? Well, notice that when we do these saving versions, the first thing that we do is we create a vector and then we fill the vector, right? Now, if we know that we're going to be solving the same dynamical system over and over and over, like you'll be doing in your homework, then you could actually hoist this allocation out, right? You can say, what the user can give me this output array, and I'll just change that output array for them. So in this form, you can say, I have solve system save bang, where the first input is, please give me the array that you want to be mutating. And so what I'll do is I'll put the initial condition in there, I'll loop through, do the computation, and I'll do the output. Right, so in this case, this ends up actually being the fastest. And when are you allowed to do this? Well, or when will this actually be faster? Well, if you're only going to call the save system one time, then the user will have had to actually do this allocation and then call your function. So you don't actually get a real timing improvement because you still have to do that allocation once. But if you're going to be solving the same dynamical system many times, then this form where the user gives you that cache vector, that is going to be the most efficient. So you kind of have to think about when, is it a common use case to call my function many times? If it is a common use case to do that, then you might want to have a version at least that hoists the allocation outwards. And in fact, once you have a version that hoists the allocation outwards, you can very easily say, I'm going to have a new version, which is solve system, where what I do here in this version is I now say I'm going to create a vector of type of u0, and I'm going to make this with undefs of the size n. I'm going to call this u, and then I'm just going to call my mutating form on that. Right. So if you want to be doing a lot of high performance computing, it's really nice to always be doing these caching forms, because you know that you want to be reusing your cache as much as possible, except when you're using static vectors. Then what you can do is, if you're always creating these mutating forms, the non-mutating form you can always make as a nice high-level function by just creating a vector, calling the mutating form, and returning it. So as an API thing, you can always have the simple version, but allow the power users to use a version that can be more efficient for certain use cases. So so that's how you would do computations on these discrete dynamical systems in a way that's fast, right? The way that you might thought of just writing down the code with a simple loop takes around, it's in 20, I forget the exact number of microseconds. Let's go up here. It was 29 microseconds or 24 microseconds, where after doing a bunch of these optimizations, we get down to 4 microseconds. So this is not a small amount of optimization, right? This is a pretty heavy optimization just by understanding a few of these fundamentals and making use of them.